All right. Good afternoon. Let's get started. So the exams, I believe most of them have been graded, and this time we're not going to hand the paper version back to you. It's just going to be uploaded to Canvas page, so you should be able to see a PDF once it's been published, and you can look at the the grading. And if there's any questions, feel free to submit a regrading request, like we have done it in the past. Any questions about the exam? All right, if not, so the plan for today is that we're going to go through some matrix algebra first, and then maybe solving system of equations using matrices, matrix equation, and also look at example with eigenvalue and eigenvector. So let me begin with matrix addition and the multiplication. Well, addition and subtraction are always together. Multiplication is a bit different. There are two types. Let's begin with matrix addition. So for example, suppose we are given a matrix A, which is 2, 2, 1, 4, and the matrix B, which is, I don't know, negative 6, 3, 4, 5, for example. Those are the two matrices given. And we can find the addition of two matrices. So A plus B will just be the sum of those two. So 2, 2, 1, 4 plus negative 6, 3, 4, 5. But before you actually carry out the addition or subtraction or multiplication, you also always want to check whether you can do it, right? You can perform the algebra. So in this case, when we add two matrices, we have to make sure that the dimensions match. So when I say dimensions, I mean the row number of a matrix and the column number. So dimension of a matrix is row number by column number. So in this case, A is a 2 by 2 matrix, 2 rows, 2 columns, and a B is also 2 by 2. So they have the same dimension, so that means we can add or subtract. To add them together, we're just going to take the corresponding elements and add them together. I can't reach, but so we take the first element of each matrix, the 2, the negative 6, we add them together, then we move on to the second element in the first row of each matrix, we add them together, 2 and a 3, and then we move on to the second row. So that will be 2 plus negative 6, that's a one value, and then 2 plus 3, that's the second value, and then 1 plus 4, and then we have 4 plus 5. So we just add the corresponding elements together, and that will give us negative 4, 5, 5, 9. So that's how we add two matrices together. Subtraction is the same. We just subtract corresponding elements. So the next thing is scalar multiplication. We can take a number, for example 5 in this case, and then we can multiply with the matrix A. So that's a 5 times 2, 2, 1, 4. When we take a number multiplied by a matrix, it really doesn't matter what the dimension is. The dimension of a matrix could be anything. What we do is we just take every element in the matrix multiplied by the scalar. So 5 times every element in the matrix. That's a 5 times 2 is 10. That's also 10. That's a 5. That's a 20. So that will give us a new matrix. The next algebra is matrix multiplication. For example, if I want to perform matrix A times matrix B. To do that, you have to be careful. Well, let me write down them first. So that's a 2, 2, 1, 4 times negative 6, 3, 4, 5. If I want to multiply two matrices together, the first thing we need to be careful about is whether we can actually multiply them together, which involves checking the dimensions of each one. So A we know is 2 by 2, B is also 2 by 2. So by checking the dimensions, what I mean is that we have to look at the column number of A and the row number of B, so they're the same. So basically, if you list the dimensions side by side, you want the two numbers in the middle to be the same. So that's how we know we can multiply two matrices together. So those two numbers must be same. If they're different, then it's impossible to multiply those two matrices. Now, what about the row number of A or the column number of B? It doesn't matter when it comes to multiply two matrices together. We only focus on those two inner numbers. So, in this case, they both are 2. Both of the column number of A and the row number of B are 2, so we can multiply them. To multiply them, we have to be careful. The algebra is, for example, the algebra we have to take the rows of A will multiply with the columns of B. So the first element will be coming from the first row of A, the first column of B multiplied together. And to do that, we take the corresponding element, so the 2 multiplied by negative 6, this 2 multiplied by this 4. Then we add the products. So first row of A multiplied with first column of B, that will give us the first element in the first row, first column position. So that will be 2 times negative 6 plus 2 times 4. So like I said, you multiply this 2 corresponding to this negative 6, we multiply them, and we're going to add this 2 times this 4. That gives us one number. But then we can also take the first row multiplied by the second column of B. So first row multiplied by second column here. So that will give us first row, second column entry in the product. So that's 2 times 3 plus 2 times 5. And we used up all the columns, right? That means we're not going to have a number in the third column here because we don't have a third column to multiply with the row. So we can close the bracket here. And we close the matrix. Doesn't mean we're done with finding the product, we just have to move on to the next row. The second row of A, we can multiply with the first column of B. So that will give us this element. This is the second row, first column, so that's a 1 times negative 6 plus 4 times 4. And then we can take the same row, the second row, we can multiply with the second column of B. That will give us second row, second column entry. So that will be 1 times 3 plus 4 times 5. And then we did most of the challenging work. So the rest is about just, be careful to do the calculation. And if we are careful enough, we should end up with, let's see, negative 2, 6, negative 12, plus 8, negative 4, 2, 3, 6, 2, 5, 10, that's a 16, and then 16 minus 6, 10, and then 1, 3, 4, 5, 23. But I would say that this is probably the most confusing part. That can get comfortable how we do that process. I always write it out first. I don't try to do everything in my head, because then if I lose track of one part, then the answer will be wrong. So it's always good to write it out clearly and then calculate the addition and the products. Questions? So that's matrix operation. What else? Inverse determinant. So the next thing we're going to do is we're going to find determinant of 2 by 2 and also 3 by 3 matrices. Let's begin with a 2 by 2. So the method that I'm going to use, I'm going to call this backward slash minus forward slash method. Basically, we draw this backward slashes and then multiply numbers on those lines, and then so you subtract the other direction. For example, if we have a 2 by 2 matrix A, which is A, B, C, D, then the determinant of A, we can use this notation, vertical line A, B, C, D. So I want to point out, you probably already know, bracket means matrices. So if you have vertical line, kind of like an absolute value sign, it means finding the determinant. So the method that you already know, it's just the backward slash. You draw a backward slash line, goes through two numbers, AD, so multiply them together. And then we're going to draw a forward slash that goes through BC. So we're going to subtract this new product, B times C. So AD minus BC, that's the determinant of 2 by 2 matrices. You can always memorize it and make it simple. And if we take the example we had earlier, so let's say A is 2, 2, 1, 4, and then the determinant of A, if the backward slash goes through 2, 4, so that's going to be 2 times 4, and then we subtract the forward slash. If I draw it, it's going to go through 2, 1, so I'm going to subtract 2 times 1. So that will give me 6. That's the determinant of A. For a 3 by 3 matrix, it's the same. I'm going to use an example here. Let's call it C. Let's see A is, or let's call it C, which is 6, negative 2, 1, 7, 3, 5, 8, negative 1, 2, for example. And if I want to find the determinant of C, now because we have more numbers, so we can just draw one backward slash and one forward slash, and that will give us that. That does not give us a determinant. So what we're going to do here is we're going to rewrite this matrix. 6, negative 2, 1, 7, 3, 5, 8, negative 1, 2. We're going to rewrite it by repeating the first two columns after this matrix. So I just draw a dotted line there to indicate that this is my given matrix, but I'm going to take the first two columns, I'm going to copy it after this dotted line. So I get 6, 7, 8, negative 2, 3, negative 1. I don't need more columns, just those two should be enough. This is what we call a augmented matrix, because the matrix we were given, we fix it by adding more columns to it. And from here, just like we did before, we're going to draw a few backward slash. The first one that will cover 3 elements is 6, 3, 2. So I'm going to multiply them together. So 6 times 3 times 2. And then it looks like I can draw another backward slash. Goes through 2, 5, 8. So I'm going to add it to the first product, so negative 2, 5, 8. And it looks like I can draw another backward slash that goes through 3 elements, 1, 7, negative 1. So plus 1 times 7 times negative 1. So those are the 3 products I can get by drawing backward slash that cover the 3 elements. Okay, so that looks like that's good. And then we're going to draw forward slashes and then subtract those products from what I have. So the first forward slash, not from the 6, not from the negative 2, 7, because they don't give us 3 numbers. It should be coming from the 1, 3, 8. That will give us the product. So minus 1 times 3 times 8. And it looks like I can draw another forward slash that goes through 6, 5, negative 1. So minus 6, 5 times negative 1. And then I can draw another one that covers 3 numbers, negative 2, 7, 2. So minus negative 2, 7, 2. So this is what I do to set it up. I know that Professor Gibson does it slightly differently, but the idea is the same. We still take this backward slash, we add them together, and then we subtract the forward slash from them. I like the way I set it up because I just kind of like, just draw those lines so I don't have to think too much. I know what Professor Gibson did is that when you work with the backward slash, you take 6, 3, 2, then you plus negative 2 times 5, but there's missing a number, so you go to the lower half to look for that number 8. And then you have 1, but you're missing 2 numbers, you go to the lower bottom left corner to look for 7, negative 1. So that's the thing. Any questions about what I did? Yep. Oh, this part?
No, not that. When we wrote it out, we had 6, 7, 8, negative 2, 3, negative 1. You didn't put the last.
Correct. It turns out that that's not necessary. So for 3 by 3 matrices, if we want to find the determinant, we just take the first 2 columns, just kind of copy it after that matrix. Then when we draw those lines, that will give us 3 numbers on each line. Okay. We don't need the 1, 5, 2 at the end because even if we have it, we continue to do it. It's just going to give us redundant products. And from here, we just have to be careful with the algebra, like carry out step by step, find each product, and then at the end put all of them together, which I don't think I have the brain power to do it now. Well, let's see. 6 times 6 is 36. Negative 2, 5, 8, so that's minus 80. And the 1, 7, negative 1, so that's a minus 7. Then minus 28. Minus 6 times 5 times negative 1, that's a positive, so plus 30. And the minus negative 2, that's a positive. 2, 7, 2, 28. Oh, not too bad. We get minus 28 and a positive 28. Oh, interesting. No, that's minus 24. Sorry, 3 times 8 is 24. I'm going to leave it there, to be honest. My brain is tired. So we get a number at the end. Any questions So that's finding the determinant of 3 by 3 matrices. That's one way. There's other ways to find it, but we're probably going to talk about it in the future. All right, the next thing I wanted to talk about briefly is finding the inverse of 2 by 2. So find inverse of 2 by 2 matrices. So suppose we're given A equals A, B, C, D. The inverse of A can be found by using this formula, 1 over determinant of A times this new matrix. The new matrix has a specific form, and coming from taking A and D, flip them, so D goes here and A goes here. And then we have to take the B, make it negative, and C make it negative. So D goes in the first place, A goes in the last position, and the B and the C stays, but they will become negative. So negative B, negative C. So this is a very specific formula. Don't get confused. And if we take the example we had earlier, A, which is, what was the example? 2, 2, 1, 4. And we can find the inverse of A, which is 1 over the determinant of A. We know, right? We found it earlier, determinant of A is 6. So it's 1 over 6. Times this new matrix coming from switching A and D, so it's switching 2 and a 4, so that's a 4, that's a 2, and then I make the remaining two numbers negative, negative 2, negative 1. So what I did is I switched those two elements on the diagonal, and then I make the other two numbers opposite. And then the last part is just multiply everything by 1/6. So that's a 4 over 6, 2 over 3, negative 2 over 6, negative 1 over 3, negative 1 over 6, and then 2 over 6 is 1 over 3 again. So this is the inverse of A. Questions? If you don't have questions, I'm going to kind of bring those together, the inverse, the matrix product. We can use them to solve a system of equations. So use matrices to solve system of equations. For example, if I have the system 2x plus 2y equals 6, x plus 4y equals 6. Obviously, we can all solve it using elimination or substitution, right? But for the sake of practice, so what we're going to do is we're going to solve it using matrix equation. So the first step, what we're going to do is we're going to convert this into a matrix equation. Which involves extracting all the coefficients on the left-hand side from x and y terms, put that into a matrix. So take out the 2 from the x, 2 in front of the 2x, 2 in front of the y, and then 1 from the x, 4 from the y. So that will give us 2, 2, 1, 4 as a matrix. So that's a coefficient matrix. We can call it A, matrix A. And then we're going to multiply by the variable matrix, which is going to be just x and y. So this is the variable matrix. and then we can call this capital X matrix. That's the left-hand side. The right-hand side, we have two values. We're just going to put it into a matrix 6, 6, and this is what we call matrix B, lowercase b. So what we did is that we take the system of equations and we convert it into this matrix equation of A and X equals B. Okay, how do we solve for x, y? How do we find this matrix x? Well, we can solve for it if we can eliminate A, right? To eliminate A there, we can multiply by the inverse of A on the left-hand side. So because A inverse and A is identity, so we get rid of A, give us x. If we multiply it to the left side, we can multiply to the right side of the equation. You have to be careful where we multiply by A inverse. It's very specific. Since we place A inverse to the left side of what's already there, so we have to put A inverse to the left side of what's already there on the right-hand side of the equation. So A inverse goes in front of the B, not after. Now the left-hand side, we have A inverse times A is identity times X. The right-hand side is A inverse times B. And identity times X is just X. So X equals A inverse times B. So that's the formula. How to find the X matrix. In the example we had this A times X equals B, so if you want to find X, we're going to say X equals A inverse times B. But we have to know what A inverse is. So that's a step 2. Find A inverse. And since I already did that with the earlier examples, so A inverse we know. That's what I had above is 2 over 3, negative 1/3, negative 1/6, and a 1 over 3. So I already did the work, but for you, if you see a problem like this, you might want to find A inverse in the process. Well, you should. And after we find A inverse, we can move on to step 3. Calculate the variable matrix X by using A inverse times B. And here we have A inverse 2 over 3, negative 1/3, negative 1/6, 1/3, times B. B is just the right-hand side of the system of equations, so 6, 6. And then we just have to perform this matrix multiplication. So that will be 2 over 3 times 6 plus negative 1 over 3 times 6. That will give us a value. And then we put the second row multiplied by this column matrix, so negative 1/6 times 6 plus 1 over 3 times 6. So negative 1/6 times 6 plus 1 over 3 times 6. So that will give us, if we do everything correctly, we get 2 from the first element and the 1 from the second element. So this is the entries of the variable matrix X. So this is the X value and the Y value. This is one way to find X, Y. There's another way which involving like a row reduction, but we're not doing it here yet. Just different ways. Does that kind of make sense? I think the homework, that's one homework problem like this, it's number 2. That would be good practice if you start working on it. Questions? All right. So the next thing I'm going to do is I'm going to take an example to find something different. It's about finding eigenvalues and eigenvectors. So eigenvalues, we usually use lambdas, lambda 1, lambda 2, and the eigenvectors we use v, v1, v2. Those are vectors. Of a given matrix. To begin the process, I want to kind of do a little bit of background. So, by definition, eigenvalues and eigenvectors satisfy the equation a times v equals lambda times v. And then we can rearrange this equation by moving the right-hand side to the left. So you have a times the vector minus lambda times the vector equals 0. And if we want to solve for lambda or solve for v, we might want to simplify this equation. We can't do it yet because here we have, well, we know that a times v is a matrix, lambda times v is still a matrix, but we cannot pull out the vector, the v from here, because if we did, we end up with a the matrix minus lambda, which is a number. So we cannot perform the calculation of a minus a matrix minus a number. They don't have the same dimension. But what we could do, we're just going to add identity matrix to that second term, because you can think about identity times v is still v. So you can think about this identity coming from the vector v there. And now we can pull out a vector v, so that's a minus lambda I times v equals 0. Because lambda times I is a matrix, a is a matrix, you can actually subtract. So here we have a minus lambda I times this vector v equals 0. And if we want non-zero vector v, if that's what we want, then the determinant of a minus lambda I must equal to 0 in order for us to have non-zero vector v as a solution from the equation. So you can think about this is a very important rule. That's what we're going to use to find lambda, and this is another important rule that we're going to use to find the vector, eigenvector v. Obviously, you don't have to find it there. You can always look for it from the sort of the definition. So, whenever you find eigenvalue and eigenvector, definitely memorize this equation and also this one. Even if you don't memorize this one, at least you know where it comes from the a v equals lambda v. So let's take an example. Let's take the example. Let's see, a equals negative 6, 3, 4, 5. It's a 2 by 2 matrix. And we want to find an eigenvalue and an eigenvector from this matrix. Let's find the eigenvalues first. So step 1. To find eigenvalue, we're going to use this formula right here. So we need to know what a minus lambda I is. So find matrix a minus lambda I. So let's plug in a, and identity, so that's a negative 6, 3, 4, 5, minus lambda, we don't know, but identity matrix, we know it has to be a 2 by 2, otherwise we couldn't subtract from a. So that's a 1, 0, 0, 1. And if we carry out the process, so that will give us negative 6, 3, 4, 5 minus lambda 0, 0, lambda, and that's going to be negative 6 minus lambda, 3 minus 0, 4 minus 0, 5 minus lambda. This is the A minus lambda I matrix. Obviously, we don't have to do this all the time. In fact, A minus lambda I is always going to be subtracting lambda from the diagonal entries, because when we have lambda times identity, we just have lambda on the diagonal, we subtract that from the A matrix. So you can think about in the future, if you want to find A minus lambda I, the shortcut is just subtracting lambda from all the diagonal entries. That'll be a quick way to find it. So that's the first step. Step 2, find determinant of A minus lambda I. Now this is a 2 by 2 matrix, so we can find the determinant relatively easily by using a formula. So determinant A minus lambda I is equal to A times D minus B times C. So that's a negative 6 minus lambda times 5 minus lambda minus 3 times 4. Expand the product and then simplify. We should end up with negative 30 plus 6 lambda minus 5 lambda and then plus lambda squared minus 12. So we end up with lambda squared plus lambda minus 42. And then we want to find the lambda, but we must make sure that the determinant of A minus lambda I should be 0. We're going to set this quadratic expression equals 0. So step 3, determinant A minus lambda I equals 0. So that will give us lambda squared plus lambda minus 42 equals 0 there. And then we can find the two lambda values. If you factor them, it should factor nicely in this case. So we got lambda 1 equals negative 7, lambda 2 equals 6. Those are the eigenvalues. Any questions on finding eigenvalues? So there's like a kind of a few steps. You have to follow them step by step. To be honest, I'm not aware if there's other approach to find it. There might be other shortcuts, but that's what I know. Just be careful, step by step. Don't make any mistakes. If you do, then the rest of the work is probably going to be wrong when you're finding eigenvectors. Questions? So that's finding eigenvalues. Now we can find eigenvectors. Basically what we do is we find in the V that satisfy AV equals lambda V, or we find a V that satisfies this one, A minus lambda I times V equals 0. Usually we use this equation instead of the original one because we have a 0 here. So let's focus on the first eigenvalue. So for lambda 1 equals negative 7, what we're going to do is we're going to find A minus lambda I, so lambda 1 I first. That's a shortcut because we already know what A minus lambda I is, right? Which is this part. So what we're going to do is we're just going to take the lambda value, we're going to put in here. That will give us a minus lambda I with lambda plugged in. So we're going to use that. So that will be negative 6 minus lambda. Lambda is negative 7 in the first part. 3 is 3, 4 is 4, and then we have 5 minus lambda, negative 7. And to simplify a little bit, that will give us this a minus lambda I. So that's a minus 6 plus 7, that's a 1, 3, 4, 12. So that's the first step. The second step is we're going to take this, we're going to put into that formula a minus lambda 1 lambda I times v equals 0. We're going to put in there, so I have 1, 3, 4, 12 times v, which is something I don't know, but I'm going to call it x, y as entries of the v vector. That should equal to 0 vector, which is 0, 0. And the step 3 is to convert it to the system of equations. So here we have the matrix equation, but I want to know what x and y are. So I'm going to take this and rewrite the system of equations from there. I already know the coefficients, 1, 3, 4, 12, so that's a 1x plus 3y equals 0, 4x plus 12y equals 0. And I get two equations, but really they're just the same equation, which is fine. It just means that, we have infinitely many choices for x or for y, but we just have to pick the one that's simple. So before we do that, let me write down x equals negative 3y. So if we were to pick value for x or value for y, well, remember that they cannot both be 0, right? It has to be non-zero. One of them could be 0 if possible, but we cannot have both of them equal 0. So from here, we're just going to pick randomly x value. Usually you try to avoid fractions if possible. So in this case, we pick y to be integers. So y equals 1 perhaps, and x equals negative 3. That means the vector I'm looking for, the eigenvector, I'm going to call it v1, is just going to be negative 3, 1. This is my first eigenvector, corresponding to the eigenvalue, lambda 1 equals negative 7. One thing I want to point out that when you find eigenvectors, often you end up with cases like this, like, you just have one equation, has two variables in it, and then you can just pick some random value for each, for one of the variables, and then figure out the other one. In that case, you always want to, you don't want to end up with some big number to calculate, right? For example, if I pick y to be 257, then I take y to calculate x, right? Or if I pick y to be some weird fraction, then I don't know, take a y times x. So you always want to pick something that's straightforward, obvious, and try to avoid fractions. Any questions about finding the eigenvector in this process? There's a lot of small steps in the process. If you practice a lot, it's going to get a lot easier. It's really not difficult work. It's just like a lot of tedious, algebra in the process, and you have to be careful not, mixing the steps. I think you should be okay if you kind of practice a bit. So that's for lambda equals -7, and then we can find the second eigenvector for lambda 2 equals 6. Do the same way. We're finding the a minus lambda I, in this case will be 2, so a minus lambda 2I. So we're going to take 6, we're going to again put into this a minus lambda I matrix, so put 6 there for lambda. We have -6 minus 6, 3, 4, 5 minus 6. And to simplify, so that should give us -12, 3, 4, -1. So that's a step 1. Step 2, we're going to find the matrix equation, which is a minus lambda 2I times v2 equals 0. Don't worry about the subscript. You can just use lambda and v all the time. So that will be -12, 3, 4, -1 times this factor xy, I don't know. That's equal to 0, 0. And in step 3, convert this into a system of equations. So that's a -12x plus 3y equals 0. And then we have 4x minus y equals 0. And again, just like before, it turns out that we really just have one equation instead of two. So we get 4x minus y equals 0, and the y equals 4x. And here you can decide what to pick for x and y. Obviously I'm going to go with the easy one, right? So if I want y to be an integer, so x has to be an integer. So x equals 1, y equals 4. That's fine. If you pick x equals -1, y equals -4, that's also okay. So v equals 1, 4, v2. This is the eigenvector for second eigenvalue lambda 2 equals 6. It's almost time, but I do want to point out one thing. Let's just say you do all this work, at the end you want to check, right? So how do we know if we did everything correctly? So to check, you can go back to what we begin with, which is AV equals lambda V. For example, how do I know this eigenvector is correct for this eigenvalue? So I'm going to take them, plug into this equation. So the A matrix, which was -6, 3, 4, 5, I believe. So that's A, and the times V, which is a 1, 4, is that going to equal to lambda 6 times this same eigenvector 1, 4. If both sides give us the same matrices at the end, or same vectors at the end, then we're good. If not, then we have a problem. So that's how we check. Which I don't like to check, but you should. Any questions?